it is. Perfect. Uh-oh. Gotta make sure I'm off my Twitch page. Alright. Alright. And I need to pull up the relevant bookmarks. Let's see. I was looking at this. I also need to go track down real quick the documents that I was reading yesterday. Not the Peacock. No. Yes, this one. There we go. Brilliant. So, let's see. I've got about an hour and a half maybe, so I'm not going to waste any time. If you're not in the stream at the beginning, you'll just have to catch it on YouTube. If you're watching on YouTube, welcome. So, let's see. This is all for coder stuff. I'll just close it so I don't have all that stuff open, and then I'll reopen it so that we can get just the TTF file reading thing that I had yesterday. Let me switch all of my other stuff over to the relevant. Okay, run is still set. Build, debug. Switch this back to the TTF builder. Okay, brilliant. Alright, so that's where I left off. Was I was able to get all of these table directory things coming out in a way that looked correct. So the next question is, what kind of tables do we have, and can I look into any of those tables to make sure that the information looks reasonable? CMap character to glyph mapping, interesting. Glyph data, font header, horizontal metrics, index to location, maximum profile. Volibus, I live in the US, but I have two different places where I sometimes stream from. But they're in the same time zone, so that's all of the details about my stream location. Anyway. Interesting. What's a font program, I wonder? Kerning, horizontal device metrics, linear threshold, vertical divide. Where is? Alright. So let me see. Tags are the names given to tables in the true type font file. At present, all tag names consist of 4 characters, though this need not be the case. Names with less than 4 letters are allowed by the necessary, if followed by necessary trailing spaces. A list of the currently defined tags follows. So these right here are the 4-letter name tags of different things. I see. So, let's see. So those are like, to clarify what all that means, if I'm looking at my table directory entry, this tag here is 4 bytes, and if I look at those 4 bytes and I compare them to these tags described here, though that means that table entry points to a table that contains data about this kind of thing, right? So this is like the list of kinds of tables I can have, and those table entries just show where those tables begin in the file. Pretty typical stuff. We've gotten used to files, and that's a pretty typical pattern that you might have. Note that these tables will not have any effect on the scan converter. Tags for these tables must be registered with Apple Developer Technical Support. Not sure what that means. Tag names consisting of all lowercase letters are reserved for Apple's use. Number 0 is never a valid tag name. Okay, table checksums are the unsigned sum of the longs of a given table. In C, the following code can be used to determine a checksum. Length. So it takes that table, rounds it up to a 4-byte length, and then rounds the length up so that it's 4 bytes, and then iterates across all of those, adding them together, and that's your checksum. Cool. Okay. Character to glyph index mapping table. This table defines mapping of character codes to the glyph index values used in the font. Defines the mapping of character codes to the glyph index values used in the font. Okay, so if I have character code and I want to know what's the glyph index in this particular font, this table does the mapping. Gotcha. The table header indicates the character encoding for which subtables are present. Each subtable is one of 4 possible formats and begins with a format code indicating the format used. Okay, Unicode encodings, platform ID 3, encoding ID equals 1, must use format 4 for their CMAP subtable. Microsoft strongly recommends using a Unicode CMAP for all fonts, however, some other encodings that appear in current fonts follow. The character to glyph index mapping table is organized as follows. Table version number, number of encoding tables. This is followed by, so this is like the top of the CMAP. Alright, we're looking at the CMAP table. This is what's at the very top is these two U shorts. So let's see if I can identify such a table. Basically what I want to do is I want to add, when I'm printing a directory entry, what I want to do is I want to say the tag shouldn't be this hexadecimal number, it should actually be a 4-byte string that you get from right here. See what that looks like. Yeah, so I don't actually want to byte invert those, which is what I was trying to figure out, because as you can see, like, this is OS/2 backwards, this is CMAP backwards, and since they're encoding those as characters, there's like, even though you can have little endian or big endian for a number, you don't have that for strings. Strings always start at their beginning and they go to their end. So like the low address of a string is even on a little endian or even on a big endian is still the first character of that string. Now there's no reason you couldn't have a format that says we start our strings at high addresses and decrease them, but they don't appear to be doing that. So that just means I don't byte reverse the tag. Alright, so that right there is the CMAP table, so that means we can have a little thing that will look for the CMAP table and find it. So the way that looks is, let me just say that I want like a table directory entry that actually is going to start at directory entries and get incremented each time. That way I don't have to do this to get my pointer. I just have my pointer. And then if the entry tag equals what I call like TTF tag CMap, no, see, like that. And then I'll pop up here and we'll do some defines. So what we need is TTF tag, and that takes 4 characters. And then it's basically A plus B shifted by 8 plus C shifted by 16 plus D shifted by 24, right? Yes. And I'll throw all of that into a thing. Throw each of these into a thing. Just gotta make sure you sanitize your macros because your code transformer doesn't exist to do it for you yet. Alright, and then CMap is TTF tag CMAP. Brilliant. Alright, so now we have a CMAP tag, and if we find the CMAP tag, I want to jump to the offset of that, so it'd be kind of like parse CMAP, and it's file data plus entry offset, right? That gets me a pointer, and now let's pop up here and say how do we want to parse the CMAP. Alright, and again, I'm just writing this program to kind of take notes on how this thing works so that I can investigate a particular example TTF file and make sure that I'm understanding how everything is laid out. I'm not actually trying to make a TTF reader that I would use. So let's see, table version number and then number of encoding tables. Okay. Version subtables. Alright, CMAP header equals CMAP header start. Actually, car star, I'll name that cursor, and then start. I'll keep the name for public facing, I guess. And there's always this tension because sometimes I want the name publicly facing to mean one thing so the people who read it know, oh, here's how I use it, but internally I use it for a different thing. So internally I'm using it for the thing I normally call a cursor. And of course what I could do is just resolve the tension that way and stop being stupid about it, because I'm sure it can optimize that out. No need to think about it. Alright, so there's your cursor, and then header +1, car star, and of course I can switch this back to being void, which would be nice. Would it? Maybe not. Maybe not. I've been finding I regret having void pointers in function signatures once in a while, so actually I'm not going to do that. Okay. So fix the that thing and then print the that thing. Oh jeez, oh Pete. There we go. Here it is. Alright, so it says here that there are 3 subtables and it's version 0 of the font. Both reasonable numbers that I could believe in. So that's good. Let's see what happens after that. An entry for each of the n encoding tables specifying the particular encoding and the offset of the actual subtable. So next we have sort of entries for the subtable. So these are CMAP subtable entries. U short, U long of platform ID. Well, let me put this over here. Get rid of this one. Alright, so we need CMAP subtable entry. Unsigned short. Platform ID. Unsigned short. Plat encoding ID. Unsigned long. Offset from CMAP. So that's not from the beginning of the file, that's from the beginning of this header. So that's good to know. Okie dokie. How about I loop over that now. Alright, for each of those, I need, let's see, we've got CMAP subtable entry, entries, let's just do entry equals, and that's going to start right here at the cursor, and increment across those, and for each one of those, I want to byte fix the entry, and then I want to print the entry. So here's how you byte fix CMAP subtable entry. You byte reverse the entry plat ID. Coding ID. And you byte inverse the offset from CMap. Then you want to print the CMap subtable entry. Alright, so this is the platform ID. Whoops, and that goes here. There's the plat encoding ID. I'll call that encoding ID. That goes there. And then there's the offset from CMap. And that goes there. Now, of course, I'm just doing %d all over the place, and that's like actually not even what I should be doing when I think about it. Gotta make sure I cast these correctly. Just to be safe. Offset from CMap. Yes, yes, yes. And then after each one of those it prints, have it printf a new line after it. Or before it, I think was actually the better option I determined. Yeah. Alright, let's see if we can look at these subtables. Yeah. So 3 different platforms, 0, 1, and 3, with encoding IDs 3, 0, and 1. Have a lot of fun. We'll have a lot of fun figuring out what those mean if I decide to look into that. And then offset from CMap. Wait, that's 28 for 2 different people. So I guess this is just saying that platform 0 encoding 3 and platform 3 encoding 1 have the same exact format, so they just plugged them together, which is kind of cool. Pretty cool indeed, actually. Alright, so when building a font, that will be used a Macintosh platform ID should be 1 and encoding ID should be 0. So this is the Macintosh one. This is the Windows one. What is this one? We do not know. I don't have a directory here of platforms and encodings or anything, which would be kind of nice. Byte encoding table. So from here on, it looks like there's at least 2 different types of tables you might get, and since I don't know how to determine which format I'm going to get, I mean, presumably this one is using this format here. Now I don't know. Okay, so probably this one and this one used format 4 here. And you can see where it'd be kind of nice to know the mapping, like they don't have the directory of all this stuff, so gonna have to say that that's enough digging into this particular table probably. Alright, so now that we've kind of got our but the good thing is these do make sense, because if you look at this, we can do a little bit of math real quick to make sure it makes sense. So first of all, the first one is 28 bytes after the beginning. So why would that be? Well, it would be because all of the structs before it add up to 28 bytes. So let's look at the TTF code real quick and see what those structs should add up to. So there's 4 bytes there, and there's 8 bytes here, and there's 3 of these. So 8 times 3 is 24, plus 4 more bytes, 28, right? So the reason the first table starts at 28 is just because this header struct plus the 3 directory structs add up to 28. So that makes perfect sense. And then this one here goes to 1228, and that fits within the length of this, right? So that makes sense as well. And presumably if we were to look at the size of this, we would know, but like I said, I don't really want to go any deeper than this on the C map, because that looks like we've kind of got I've gotten a hang of how this is doing things. It's not lovely that I don't know how to translate to which table I want to look at, right? Like which format that appears to be information that they just didn't list here. Maybe I could look it up somewhere else, but I don't need to dig into this. I want to see where's the hinting information in a TTF. Right, this is in a GASP table. Alright, and of course I wouldn't have known. See, here's why I was digging into it. I've already searched to this point once before, and I didn't know what this GASP meant. Now I know what that means, because I've been looking into how this stuff works. So that's a good thing. Now let me take a quick look at my output and see if I have a GASP table. GASP, right there. Awesome. So we're going to dig into this table, because this is the one I care about. So I'm going to need the tag so I can identify it. Very cool. Okay. Well, let's take a look at it. This table contains information which describes the preferred rasterization techniques for the typeface when it is rendered on grayscale capable devices. This table also has some use for monochrome devices, which may use the table to turn off hinting at very large or small sizes to improve performance. Turn off hinting? Wait, what? Maybe that's not what I want, but let's keep going, because that might just mean the hinting information is in there, and they're saying that in a weird way. I don't know. At very small sizes, the best appearance of grayscale devices can usually be achieved by rendering the glyph in grayscale without using hints. I wonder if hinting shows up anywhere else. Hint, hinting, hinting. Is this still inside of GASP? Composite glyph description. Simple glyph description. No, this is under something called glyph. This table contains information that describes the glyphs in the font. Each glyph begins with the following header. I think this is the table I'm going to end up caring about. If that, this forces the AW and LSB for the composite to be equal to those from the original glyph. This works for hinted and no, this is not actually it. Okay. Smallest readable size in pixels. Fully mixed directional glyphs, only strongly left to right, like one, but also contains neutrals. This table gives global information about the font. The bounding box values should be computed using only glyphs that have contours. Glyphs with no contours should be ignored for the purposes of these calculations. That's the direction of hinting. Note that max style bits must agree with OS2 table F selection, but are used the panos values and post. Sorted order, sorted by. Wait a minute. Under Windows, the US Win SN and values from OS2 table will be used to determine the maximum black height for a font at any given size. Windows calls this distance the font height because true type instructions can lead a font to font heights that differ. Okay, 1 minute. I might have misunderstood something here. Canuckles, the documentation's actually pretty good. I think the thing that makes TrueType complex is that it supports a lot of different platforms that want different information. So, like, there's a ton of information in a TTF. Yeah, so it seems to me that hinting is not just a straight up number that they store somewhere in the file or an array of numbers. So what I've got over here, the Apple TrueType reference manual. Okay. So insofar as just giving me the tip that it might be the interpreted language that does hinting, because it looks like all the information I found there was like related to hinting but didn't actually do hinting, which means I was on the wrong track with this and with this. That's fine though. I don't mind having to look into something else. Interesting. Interesting. This is intriguing to me. The word hint doesn't show up in here though. Font hinting, also known as instructing, is the use of mathematical instructions to adjust the display of an outline font so that it lines up with a rasterized grid. At low screen resolutions, hinting is critical for producing a clear, legible text. It can be accompanied by anti-aliasing and subpixel rendering for further clarity. So yeah, they use it's using this instruction, this interpreted language, it looks like. Optimal results. A font instructor should follow these guidelines. At small sizes, chance effects should not be allowed to magnify small differences in the original outline design of a glyph. At large sizes, the subtlety of the original design should emerge. There are 3 possible ways to hint a glyph. The font contains hints, in the original sense of this word, a guide to guide the rasterizer, telling in which shapes of the glyphs need special consideration. The hinting logic is partly in the font and partly in the rasterizer. More sophisticated rasterizers are able to produce better rendering results. Okay. The font contains exact instructions, also called bytecode, on how to move the points of its outline, depending on the resolution of the output device, and which intentionally distort the outline shape to produce a well-rasterized result. Is in the font. Oh, this is more complicated than I thought. Let's see, got a link here from insofar as. Ever since software developers and typographers were given the task of rendering scalable type on low-resolution devices, the hinting problem has been acknowledged. The problem, much more noticeable with scalable type than with other scalable graphics, reflects the high demands for visual consistency the IA makes on type. The mathematically correct pixels for character outlines scaled to a given size and resolution are often unaesthetic or illegible. Hinting is the name for the set of techniques used for restoring, as far as possible, their aesthetics and legibility. Interesting. In general, hinting consists of careful and usually small adjustments in the outline filling process. At low device resolutions, undesirable rounding effects mean that parts of some characters can disappear and other parts can appear too thin or too thick. Hint attempts to correct this by equalizing the weights of stems, preventing parts of glyphs disappearing, and generally maintaining aesthetic appearance and legibility down into as low a resolution as is possible. Hinting is at the heart of TrueType. Its inventors, mindful of the diversity of opinion on the correct way to hint type, decided there was no single hinting paradigm that they would impose upon type developers. Instead, they linked a relatively simple rasterizer to a new interpreted programming language. Each glyph in the font contains its own little hint program, with which the control points of the outline can be manipulated just prior to rasterization in any way the hint programmer desires. In practice, this means that the outline is carefully distorted by each glyph's hinting. This is such an interesting little adventure I've picked. I'm excited, I'm very excited to look into this more. In practice, this means that the outline is carefully distorted by each glyph's hinting instructions to surround only those pixels that produce the desired bitmap image. The language includes loops, conditional branches, user-defined definable functions, instructions to move, align, and interpolate points in various ways, often with reference to control values, methods to round points to the grid of the device. Oh my goodness. Oh my goodness. Okay. TrueType hinting language is stack-based, like PostScript, in that the instructions take all their arguments from the stack. Instructions take form of single byte codes. Push instructions to push by words. Okay. Also, like PostScript, there are no actual drawing instructions, only instructions that move existing control points. The TrueType hint editors, such as type main, hide the stack-based nature of the language from the hint programmer. letting one edit in each instruction alongside its arguments. Interesting. Glyph scaling. Before any hints are applied, the glyph is scaled with respect to the current ppem, pixels per m. So m in the s in the box thingy. Okay. This value is a measure of the number of pixels available for rasterization, derived from point size and resolution. Okay, the graph. So it's basically saying if we want a font of this size and we have this resolution, how many pixels do I have to render for here? Because that'll determine the grid I need to work in, and then off the program goes fixing the font. All the glyph's coordinates are now measured in fractional pixels rather than integral font design units. Coordinates are F26.6 values, 32-bit fixed point numbers with 6 fractional bits. Okay. Each point is stored twice. Once for its original position, once for its current instructed position. Okay, so you have two pieces of information that each point knows: where it started, where it is after this, and where it's been moved to by the program. Alright, moving points in the projection and freedom vectors. There are instructions for absolute and relative movements with measurements taken from the stack. Okay. One key aim of hinting is to maintain the spirit of a typeface throughout all its letters. This is the purpose of TrueType's control value table, CVT. It should contain measurements that are used frequently within the hints for each glyph. The CVT is always scaled to the current ppem. Sample CVT entries might be: how thick are vertical stems, how thick are horizontal stems, how thick are the serifs, by how much do round features overshoot the baseline. Interesting. Okay, so I believe we have a CVT table, right there. So I would be able to look in there and see what's going on. Functions or subroutines make the program smaller and more manageable. In TrueType, functions can be tied into the font program. FPGM table. FPGM is the font program. Okay, or the CVT. Okay, so I want to look into FPGM, but not in the glyph program. Font program, CVT. So there's a lot of little programs everywhere in this system. Okay, this is a really good link insofar as thank you. So it looks like there's a font program, which is one program for the whole font, a CVT program, which presumably takes into account all of this CVT information, and then there's still the program per glyph, and those cannot do function definitions. Characters are rasterized in a font. The font program table is executed. Okay, so first you execute the font program table that might define some functions and stuff. The font program only contains function definitions. These may be called from the CVT program or from individual glyphs. Right. Hello, Connor Rents. Let's see. The CVT program. Okay, executed before any glyphs at the ppem are rasterized. Many define additional functions or redefine existing ones, although instructions that move outline points are illegal in the CVT program. You can set points in the Twilight Zone. Well, I skipped Twilight Zone. I'll have to go read that one. The CVT. Okay, let me read this again. We call the CVT prep from individual glyphs. So the font program is just to define functions. These may be called from the CVT program or from individual glyphs. The CVT program executed before any glyph at the ppem. Any glyphs at that ppem are rasterized. May define additional functions or redefine existing ones, although instructions that move outline points are illegal in the CVT program. You can set points in the Twilight Zone. Okay. What's up here? What is this? Often it's convenient to manipulate points that are not part of the final outline, yet are useful to take measurements from. In TrueType, the Twilight Zone refers to the set of such points. Okay, so these are like variables that aren't a part of the input-output, but are just storing other stuff. They are often initialized in the CVT program. It's also useful to have a place for arbitrary temporary variables. The storage area, an array of 32-bit values, is used for this. Values in each font's max P table declare the number, toilet points, and storage locations. Okay. So, what I want to do is, I've seen the name of a lot of important looking tables here, so I'm going to put all these tags in and put a note about what they do so that I go read them. So CVT, space. There's also FP program. Up there they mention something called the max P table. Alright, I want to read a little farther, because they said there are multiple ways of hinting. And I don't know if they were just saying, they said there were multiple ways, so they did a scripting language so you can do whichever way you want, or if that's one of the multiple ways. The same TrueType code, if well written, can deal with a wide range of sizes. The best fonts also use the delta instructions to nudge control points at specific sizes. These are the form at 12 ppm, pixels per m, move control points 5 by 1.25 pixels. Paying respect to P and F, the CVT values can be adjusted by delta instructions, normally from within the pre-program. Some glyph features are extremely difficult to hint, especially with very complex glyphs, or when glyphs are rotated. Indeed, hinting rotated fonts is not well explored. Interesting. In these cases, it is useful to switch on TrueType's dropout control. A relatively slow means of ensuring delicate glyph features do not disappear entirely. Okay, well that's not very informative information, but okay. Yeah, it did mention a prep table. Refers to the set of such points. They are initialized in the CVT program prep. Let's see. I did not interpret that as being a table, but it totally could be. Oh yeah, prep. Okay. So we need to look into the prep table. Oh yeah, here's another mention of the prep table. Alright. So, you might imagine that running this program wastes a huge amount of time when displaying characters, and displaying characters is something you definitely don't want your computer to stall at. Avoid holds up by use of a font cache so that I don't really care about how to do, like I'm not trying to make a thing that redoes these programs every time it renders a font or something like this, right? I'm not trying to dynamically do, my plan is just to have, for loaded TTF, make some, rasterize the fonts once and keep that. Which yeah, it might be frequently used values, most importantly character widths at common sizes. This cache expands and contracts dynamically. Okay, that was pretty useful. So, looks like what I really need to get into is this instruction set, in fact. So, let me take a look at all of these tables and see if that is everything that I need. I don't see in here if necessarily, I shouldn't have closed that because I might want to look at it again. Where is the per glyph programs? Where are the per glyph programs? Glyph scaling. Okay. Well, I don't see anything in there, but let me look through this doc, which does sort of go into detail about each table, and see if FPGM. So there's FPGM, CVT, prep, maxp. They're all there. I wonder if it's in glyph. This table contains information that describes the glyphs in the font. Each glyph begins with the following header: xmin, ymin, xmax, ymax. Note that the bounding rectangle from the character is defined as the rectangle with the lower left corner of xmin, ymin, and the upper right corner of xmax, ymax. Okay. Perform better if the glyph coordinates have been created such that xmin is equal to the LSB. For example, if the LSB is 123, then xmin of the glyph. Yeah, I understand what equal means. This is not a particularly useful sentence. If the LSB is negative 12, there should be... Yes. Again, I understand what equals means. Again, I understand what equals means. If all glyphs are done like this, set bit 1 of flags field in the head table. Okay. Simple glyph description. This is the table information needed in number of contours is greater than 0. That is, a glyph is not a composite. Okay. So if we have some actual points that make shapes, this is where the glyph descriptions actually are for that, the actual points and stuff. Array of last points of each contour, n in the number of contours. Okay, interesting. Total number of bytes for instructions. So this is actually where, yeah, the instructions are right here. Array of instructions for each glyph. N is the number of instructions. Interesting. So I actually need to look at the glyph table for the per glyph programs. Okay, cool. So I want to see if I can get my hands on those instructions from the glyph table now. That's what I'm going to do next. So to do that, let me pop down here and say parse glyph file data plus the offset. Okay. I could not have predicted that this would involve writing an interpreter, but I'm very excited that it does. That makes me all the more reason to have done this. Alright, so we have a short num contours. So it's signed so that negative numbers means composite glyph, which is interesting. F word, what does that mean? Does that mean like a fixed point? No, it doesn't mean fixed point. Does it mean floating point? F word, there it is. 16-bit signed integer that describes a quantity in F units. Okay, so 16-bit signed integer. This is the takeaway from that. And the F units, if I recall correctly, right, okay, smallest measurable distance in the EM space. So it's like if you took this times this, you would get like positions in some kind of absolute space or something. Because you pick some kind of small grid that you put this on, and you can change the resolution of that. Presumably per glyph or like per font or something like this. But let's go back to the glyph table. No, there it is. Okay. Alright, so we have a 2-bit signed short and then 4 more 2-bit signed shorts. Okay. Alright. So it's all just these xmin, xmax, ymin, ymax. Then we need to byte fix that. Okay, and then we need to print that. I guess they must all have the same F unit because that is like not per glyph, that's a header for the whole thing, right? So that's like X min X max across the whole, Y min Y max across the whole set of glyphs, like the whole font. What? Wait, no, each glyph begins with this information. Contains information that describes the glyphs in the font. So what I'm missing right now is the number of glyphs. And I wonder if I have that somewhere else. Because it's not in the glyph table. Okay, so that's just some defined values. This contains a list of values that can be referenced by instructions. Sure, trimmed table mapping. Huh, man. So it looks to me like you can't just ask how many glyphs are there total and just look at them, because it assumes that you're like getting glyph IDs and you use those as offsets from the base of the glyph table, right? So there's actually no header here. That's just like this is per glyph, and if you don't know how many there are, then you're kind of SOL. So like there's probably one there, but oh, here's how you can tell. There's always a format integer at the beginning that tells you which format you've got. Alright, we can continue the CMAP stuff, because it looks like we're going to have to. Okay. So you see what I just saw is each of these have a unsigned short at the very beginning that tells you which one you're looking at. So when I do parse CMap and I look at that entry in the CMap, what I can then do is say, let's see, I want to look at this entry and say, look, if entry index mapping. CMap, right. Okay, so if platform ID equals 3 and plat encoding ID equals, what is it? 1. Then okay. And that means the next thing I want to do is parse what are these called here? Like a CMap subtable or something. Table. And that CMap subtable starts at start and goes to entry offset, I believe. Start. And then the first thing, whoops, what was that? And the first thing I want to do, after I've got my cursor, is take a look at this format right here. Byte reverse it. And then say we'll print that so I can see what kind of thing I'm looking at. Oh shoot. Offset from CMap. Glyph header. Glyph header. There we go. So that's looking at the first glyph in the glyph table. As I said, we don't have any way of knowing how many glyphs there are, apparently, from what I can tell. But we can see here that the table that that's pointing at is format 4. So I'll start by writing the reader for that format. Okay, this is the Microsoft Standard Character to Glyph Index Mapping Table. This format is used when the character codes for the character represented by a font fall into several contiguous ranges, possibly with holes in some or all of the ranges. That is, some of the codes in a range may not have a representation in the font. So we have sort of like large ranges where like, oh, a bunch of these are the same, but there might be little holes in the range, and then here's another huge range we have, and the gaps between those ranges are large, but we say here's a range that's mostly contiguous, here's a range that's mostly contiguous, and there's little holes in the ranges. Okay. And of course that raises the interesting optimization question: how do you pick your ranges such that you optimize on certain thing, like fewest number of ranges is a thing you want, but also like fewest number of gaps, like some sort of weighted thing there where you don't want too many gaps but you don't want too many ranges, and you get some sort of trade-off for each. It's kind of interesting. Anyway, the format-dependent data is divided into 3 parts, which must occur in the following order. A forward header gives parameters for an optimized search of the segment list. So, segment list. What is a segment list? Did we already define a segment list? Did I skip defining a segment list? I don't know if I know what a segment list is. Some of the codes in a range may not write. The format-dependent data is divided into 3 parts, which must occur in the following order. For parallel arrays describe the segments. Variable length array of glyph IDs. Okay, that doesn't really make any sense. I think it's describing this data structure that's better described by the table for some reason, so that's like, don't need that, because the table will make more sense. But basically what we need here is a new struct to describe this data. So this will be like CMAP subtable format 4. Starts with a format, which should always be 4. These are unsigned. Length of the subtable. Version of the subtable. 2 times the segment count. Segment count 2. Unsigned short. Search range, and that is defined to be, oh, what do they mean by 2 star I wonder? But if you take log base 2 of the segment count and you floor it, so you're getting like, if you took the high bit off or something, right? Unless it's a 1000 situation, and times 2. I wonder if they just mean times 2, or if that's like power of 2, like 2 to the power of that. So it's like, it's close to segment count. It's rounding. What they mean to say is least. They mean to say least power of 2, I bet. I mean, I'm guessing what they mean to say is least, or greatest power of 2 under seg count, is what I think they're going for there. Times 2. That's what they call the search range. Oh, there it is. Entry selector. That's log base 2 of the search range divided by 2. Okay, great. That'll just be basically floor log 2 of the seg count, if you think about it. The range shift. This is where it gets weird, because the segment count determines what comes next for each segment last. Interesting. So that's as far as I can go here. Which I believe that's the forward header. After that, there's this stuff. One segment for each contiguous range of parallel arrays. Describe the segments. So there's the 4 parallel arrays, a variable length array of glyph IDs. Okay, so we can call this the subtable format for header. And let's see. If, well, we'll do a switch, because who knows, maybe someday I'll want something else. But if I have format 4, then I want to do parse cmap subtable 4 from start. Cmap subtable format for header equals, need that whole pointer again, cursor equals car star header plus 1, and then I need to byte fix this header, and of course the trick is not to byte fix the format, because that's already been byte fixed. That's already been fixed earlier. Cmap subtable format for header. Let's see. I'm going to byte reverse everything in there. Header, except for that, format, length 2, version, segment count 2, search range, entry selector, range shift. Version, segment count 2, search range, entry selector, range shift. Yeah, I don't really know what they mean by all of these things. Like, they're a little bit confusing to me. What they have that in a lot of places, and I don't know what I'm looking at when they do that. And then I will print the header, and that will print cmap subtable format header 4. And for each one of those, I'm gonna length %d new header length 1 2 3 4 5. So an idea just occurred to me about why they want search range. If I understand correctly, the number of segments, they're rounding down to the nearest power of 2 below segment count, and then multiplying the whole thing by 2, which it just adds 1 to the floor, which means they could have just multiplied 2 in the segment count, like they did with seg count x2, but you get whatever. But the point is, that gives you the number of, like, the largest, that gives you a single bit at the spot where you don't need any more bits than that. So if you're like trying to compress something so that you only store exactly the right number of bits, and you say, oh, here's how many bits we're storing for these numbers, and then you sort of pack them in and use the extra bits for other things, then that's useful information. It's kind of weird you'd include it. I imagine that's not the right reason to include it, but I think that's one thing you could do with that. Anyway. Alright, I'm a little low on time, so hopefully I can run this and see what we need to see. Length 1200, does that make sense? 1750, yeah, and yeah, it actually makes sense because now we can see that, you know, this starts at 28, this starts at 1228, the whole length is 1200, so that makes sense. Version 0 segment count doubled, it's 184, that means there's 92 segments. You take that and round it down to the nearest power of 2, they got 128. The entry selector is 6, whatever that means. Entry selector. Yeah, that right there would be the number of the highest bit you actually need. It's really weird naming, but again, that would suggest that it's like, oh, you need 6 bits to store this information. For whatever reason, you might want that. Range shift. 2 times the segment count minus the search range. That's how high above this number it can go, basically. Roughly. So, that is our header for this table. Now, I want to look at these, because you can't get these without the segment count, but now we have the segment count, it's 92. So, where am I parsing subtable for? Right here. Okay. So now the segment count equals the header's segment count 2 divided by 2, aka bit shifted down 1. Alright, and then with the segment count, I can do and these are all unsigned shorts. So let's see, this is the end count. End count. It's more like, yeah, that's a really bad name, I think. It's just start character or start end code, right? And that's unsigned short at cursor. And then cursor plus equals, or cursor equals car star plus an end code plus the number of segments. Alright, and then let's see, now we're at the 0, so that's a reserved thing there, so we can take cursor equals cursor plus the size of an unsigned short to get past that. And now we should be looking at start caret codes. So unsigned short start code equals unsigned short star cursor. And the cursor now equals the start code plus the segment count. And then ID delta. So let me pull out all of these arrays up top actually. Unsigned short end code, start code, unsigned short ID delta, star, ID, range, offset. Then I don't need that. Boom. I don't need that. Boom. ID delta. Boom. Again, just one last boom there for emphasis on the boom. And then we advance the cursor. Segment count. And then glyph ID range offset equals this again from the cursor, and the cursor advances one more time. ID range offset plus the segment count. Okay, now we have this sort of structure of arrays. Actually, now that I put it that way, let me call this the CMap format for subtable format for segments, and unsigned short end code, start code, and basically this code here just up there, and then CMap subtable format for segments. Segments, segs, take the segs, drop it right there, and then just segs dot everywhere. Okay. And now that I have that, why don't we just do the loop across it and print that all out? So it's like print segs I. Don't have JAI yet, which could handle that in a slightly nicer way, but what can you do? End code I, end code, start code, ID delta, ID range offset. Delta, ID range offset. Alright, and so then my other rule is I always new line there, and I probably need to make sure to byte reverse all of that too, which is new. So once I've got all them, let's do void byte fix the segments. And of course, to byte fix the segments, what I need to do is loop across. I have to know the segment count too, really. I could byte fix the way I did the other things would be more like this, right? I byte fix right here, segs I. It's not really the... Yeah, I don't want to do that because it's not the good data-oriented way. I know that they're in caches, so I'm just going to pass in the segment count here, and it's nicer. I is less than the segment count, plus I. Alright, segs end code plus I2 byte reverse. Right, so that gets all of those byte reversed. 384. Yep, that's close. And of course, this is probably not all that good anyway, because byte reverse is a somewhat complex function, so it doesn't matter that much now. But this puts it really close to the form where if I wanted to turn it fast, I could. And of course, this is throwaway code, so none of this talk actually matters at all. But there you go. That's the nice data-oriented way to reverse all those bytes. Alright, and then we can print everything and byte fix the segs beforehand with the segment count available. Okay. Okay, 1 minute. Got to go to the build file, list what we got here. Forward TTF. Alright, I want to delete all forward TTF stuff because something is messed up. There we go. Back to the code. This will be the last run I can do. Here we go. Run. Alright. That's more segments. Oh wait, no, 92 segments is right. Yeah, so there's 92 different segments. They all have a start and end position. Like this one just starts and ends right there. There's 2 right there. They've got those. There's just like nothing. ID delta 1. ID delta 1938. I wonder what that means. It's like if you add 1, you'd get 65536. What if I add 1938 plus 64258? It's larger than that. 66196, right? So that's not just finding 65536, which wouldn't be all that useful really. So I wonder what that is doing. 9824, 9827, 9827. Yeah. Well, what I really need to do right now is just see more of that. So, see if I can remember how you find more of your output. I think it's like that. No, that doesn't do it. Unless that could have done it, and I just can't tell because this is the first round. And then no, okay. That appears to have done it. Okay. So you can see the segments right here start from 32 to 126, which is kind of like the range you'd expect for like... I wonder... if 65507 plus 32, 65539, still not totally understanding, but okay. That one has an ID delta of 0. ID range offset 0. ID range offset 182. Oops, sorry. Well, I imagine that all this information is somehow about, given a Unicode value, how do you use ID delta and ID range offset to find the correct code in the array. I just don't know how that works, really. But you can definitely see that we've got like the range of normal characters there, and there's these ranges here at the beginning that aren't just like 1 or 2 characters, and then pretty quickly we get into just like, oh, here's a few, here's a few, here's 1, here's a 6 or 7, here's 1, etc. So that looks like an inclusive range, probably. Start code and end code, along with an ID delta and an ID range offset. Well, I think this will have to be it for today. Thank you for joining me. If I find time later today or at some point in the future, I'll pull this up and we'll keep looking at looking into the TTF file. But for now,